All right, so we're looking at the 12 basic functions. So A says 9 of the functions have domain, the set of all real numbers. Which 3 do not? So we have 9 functions that have a real domain. Domain has to do with which variable? X. So if I go like this and I'm looking at it, I can see that all the X values are there. If I went over here, it would be there. If I went to infinity, it would still be there. So that one's all real. The parabola does not go straight up and down. It is going out at a slight slant. So this is also going to infinity. So on the x-axis, those would be all reals. If I go to the cubic, again, I don't see any places where a domain, this is slightly going out as well to infinity. So it's going out, 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 out. Nothing wrong with that one. Looking at the absolute value. So we're looking for 3 functions that don't have all the reals in the domain. Continue looking at the pictures to see which 3 would not have the domain of all reals. There's something wrong with it. It's broken up, something. Hey, give me one, Ainsley. Which one doesn't have the set of all real numbers? Very good. So if I look at the square root starts at 0 and goes to infinity, and there's nothing on the negative sign. So the square root of x. So A, we have the square root of x. F of x equals the square root of x. There's 1. Very good. The reciprocal function is broken at 0. It comes in and it's riding along the 0, but it never actually crosses over. So I would say yes. F of x equals 1 over x. And if I wanted to test that to see, I'm going to graph it. And, even if I zoomed in on this, zoom in is 2, and then I hit enter. Even when I zoom in on it, it's not really clear. But if I go to my table of values, what's happening at 0? It says there's an error there, right? What at 0, if I plug in 0 right here, what is this going to say? 1 over 0. It's undefined. That means there's an asymptote there. Okay, so that's why that one is there. We checked the calculator. It says there's nothing there. We substituted in 0 and said, hey, that's undefined. So we know that there's no numbers there, no real numbers. All right, there's one more. I would say yes. We'll be learning about these functions this year. F of x equals ln x. All right, so that takes care of A. B says one of the functions has domain, the set of all real numbers, except 0. Which function is it, and why isn't the 0 in the domain? Which one of these has the set of all real numbers except 0? It is the reciprocal function. We just talked about that. So it's the reciprocal function. That would be f of x equals 1 over x. If x equals 0, that would be 1 over 0, then it is undefined. Calculator says error. So we check 2 different ways. All right, C. Which 2 functions have no negative numbers in their domain? Which 2 functions have no negative numbers? Logarithmic. The natural logarithmic, you can just say ln. And so that would also be f of x equals ln x, the natural logarithmic function. And then it says, of these 2, which one is defined at 0? Which one's defined at 0? So it's not undefined. Because what's the square root of 0? That's a real number, yes. I would square root of 0 equals 0. Therefore, defined at 0. Only 2 of the 12 functions have points of discontinuity. 2 of them, discontinuity. What does that mean? Yes, I can't draw it without lifting my pencil up. And you would think it would be one of those, yes? How many did they say? 2. The greatest integer function I cannot draw all in one. So I would say yes. F of x equals 1 over x. F of x equals. All right. That is true. Are these points in the domain of the function? I'd say no, because if I was going to write the domain of the reciprocal function, if I was going to write the domain of this one, I would say it's going from where to where? From negative infinity to where? It's going from negative infinity to where there is an asymptote that's here. Well, and does it include 0? No, because it rides along that asymptote but never ever crosses it or touches it. So I would have to say no. Are these points in the domain? No, I would not say the domain includes 0 on that one. So I would say no. But this one's different. So no for this one. No for the reciprocal function, but what about the integer function? When we look at the greatest integer function, if this is -3, all the fractions, and then at -2, it's here. So just because I couldn't draw it without lifting my pencil doesn't mean all the numbers are not in the domain. So I'm here at -2, and then I go over to -1. It's got an open circle, but when I look above it, it is filled in there. So every domain number has all the fractions in between. So I would say yes for this one. All right, example 3. We're looking for 3 functions that are bounded above and below. So bounded means above and below. Which 3 functions would be bounded above and below? Yeah. So the thing about sine and cosine, I know we haven't got there yet, but look at the starting point of them. One of them starts at 0 and the other one starts at 1. That's the difference. The waves may look the same, but their starting points are not the same, and that makes all the difference in the world. So the sine function starts at 0, and then it's just like you are above, and then you are below. So the sine function is a wave that starts here, sine of x. Cosine starts at 1. And yep, they say that one is. So very good, Hannah. The logistic function, this one right here. All right, example 4, looking for symmetry. 3 of the 12 basic functions are even. Which are they? Looking for symmetry. Even. Remember that it says that you are going to have symmetry to the y-axis if it's even. You could also have symmetry to the x-axis, but it's not a function when it's going that way. So does that one have symmetry to the y-axis? That's what it said if it was going to be even. I'm going to start with the first two. We have this one, 3, 2, quadratic. I call them that the squaring function. See, these are all weird names. All right, I'm going to use it though. Squaring function, which is x squared. And the other one was the absolute value. Oh, well, you know what? I'm thinking cosine maybe. Is that seems to have symmetry. If I folded it in half, would it land on itself? I would say so, but I'm going to. Cosine starts above the axis. Okay, this is graph the function, and I didn't put a graph there for that one. Man, boy. What is this function? It is the squared function. So we're talking about x squared. Is it facing? So we're looking at either this or this. Those are the two possibilities. Which one is it? Very good. There's no negative in front of the x, so it's going to be definitely facing upwards. And then this one is in a form where we can tell where it's shifting around and what the translation is on it. So we see that it's being shifted on the x. Remember, y equals x minus h squared plus k. hk is the vertex. So we can see that there's a shift on the x. We're going to 2, but it's not being shifted up or down because there's no number. I could say plus 0, so I could just say that the vertex then was at 2, 0. So I see that it's being shifted over to 2, and if I just plugged in 1, 1 minus 2 is negative 1 squared is 1. This is the vertex. And it's going to have symmetry, so it's coming down, it bounces off. So at 3, I'm pretty sure it's going to be 1 because they have symmetry. So 3 minus 2 is 1, and 1 squared is still 1. So it does have that symmetry. All right, we can answer the question now. A, on what interval is the function increasing? On what interval is the function is it decreasing? So answer A, you can, this is kind of practicing from the homework that we just had. What interval is it increasing? What interval is it decreasing? Okay, so you do increasing. What interval is it? And what kind of brackets do I need? So do I put a square or a rounded bracket? Because in Ainsley, on which interval is it decreasing? Very good. So negative infinity with a rounded bracket to 2. Is it actually decreasing at the number 2? No, it's not. That's rounded. Do you think it's increasing at 2? No, that's the point where it stops and turns. It's coming down, it stops. So I would say rounded bracket for 2. It does not include those numbers of increasing and decreasing. Now, if I was writing the domain, yeah, it would include it in the domain, but not as an actual motion of decreasing and increasing. So those are rounded brackets. Is the function odd, even, or neither? How do you know it's even? Okay, but they didn't really talk about the tails in that way. What we have to give something that they're specific, because sometimes because there's symmetry around the y-axis, right? That was one way to see if it was even. The other one was to substitute a negative x and see what you get back. So if I can a banana, no more. Looking at this problem with symmetry, you're seeing that you have 1, 1, and then 4, 4, 9, 9. Do we have that on the function we're just working on? Do we have that? If we look at the graphing calculator, do we have that same kind of symmetry? What's the difference between this function that we're working on and the one that was in the notes? So I guess to have perfect symmetry, you literally need to have both numbers, 1, 1, 4, 4, 9, 9. Doesn't have 2 zeros, so this one is not symmetry. It's not. It has to be at the origin. Has to be at the origin. Example 6. Which of the 12 basic functions has the following piecewise definition over separate intervals of the domain? So a piecewise function is pieced together. The first function says f of x equals x. But it has a condition with it. It says that this line is going to exist if x is greater than or equal to 0. So where doesn't the line exist? Erase on your paper right now where it doesn't exist, because it says it only exists when x is greater than or equal to 0. So part of this line from here back doesn't exist because x is greater than 0 would start at the origin. So that is where that is. Try the second part now. It says f of x equals negative x. What does negative x look like? Well, that would be the negative slope coming at your 45-degree angle over here. F of x equals negative x if x is less than 0. It exists when x is less than 0. So where doesn't it exist? It doesn't exist when it's greater than 0. It says it exists if x is less than 0. So from 0 back, it exists. It does not exist when x is greater than 0. So I erase that part. That's how you sketch piecewise functions, is you sketch it regular, and then you erase whatever condition it doesn't follow. Now, what does it say? Which of the 12 basic functions has the following piecewise definition over separate intervals of its domain? Well, what function is that? That's the absolute value function. Example 7, defining a function piecewise. Using basic functions from this section, construct a piecewise definition for the function whose graph is shown. So we're working backwards now. They gave us the piecewise, we graphed it. They're giving us the graph, we have to create the piecewise. So I know that f of x equals squiggly bracket. Find a function that would be for the first part. Here's the first part. We want to write an equation for that. First of all, I have to figure out which function that it is. But this has a curve to it. It's not really a straight line. And if I thought it was like the first one, I could substitute in. When x is -1, when x is -1, it's still going to be -1. When x is -1, it'd be down here. So you do still have to substitute in some x values to make sure it works for your function. Which function looks like that first part? The whole thing's not there, right? Because they've erased part of it. So let's try it. -1, what's -1 squared? 1. So I look at I look at 1 and it's there. Try one more. How about -2? What's -2 squared? So it looks to me like that looks like the x squared function. I would agree. So we would say it's x squared if, now we have to write the condition for where does it exist. If what? X is less than 0. Yep. Oh, it only exists if x is less than 0. Now we need one more function to describe this piece. Very good. I would agree. So this is x squared. And I'm just going to check that to make sure. The square root of 1 is 1. I can see that point right there. The square root of, what am I going to pick next? I checked this. Is that a perfect square? So the square root of 4 is, and that looks exactly where that's lining up as well. So I agree. Square root of x if, perfect. So it would have to be, does it exist at 0 right here? Are we seeing a function that's at 0? We do. We do. So one of these, it can't just be less than 0 and greater than 0 because that means you're not at 0 at all. Working up to this part right here where we can fully describe any function. You're going to see, you could have a quiz just like this. You have a function, and then you have to talk about all the characteristics of that function. So, which function did they give us? Good, a nice easy one. Absolute value of x. Absolute value of x. So when x is, we'll go from, just do -2, 0, and 2. Y equals the absolute value of x. So the absolute value of -2 is 2. The absolute value of 0 is, and the absolute value of 2. And I'm just going to plot those points. The domain of this function is what? Good. And the range? Very good. It includes 0 in that range. Discontinuous or continuous? Continuous. Where is it decreasing? -infinity to 0, both rounded brackets, and increasing 0 to infinity. And here comes my favorite one, symmetry. I would say yes, that it has even symmetry. And then bounded or unbounded, what does it mean to be bounded? It says that if you're bounded below, that there is some number b that is less than or equal to every other number in the range. So you're looking at the range, there's some number that's lower than every other number. And that would be true for above as well, that there's some number b that's greater than or equal to every other number in the range. And then it's bounded if it's both of them. If you have a high and a low number, that it's staying between. So is there some number in the range that's lower than or equal to every other number in the range? Yeah, right here. At 0, and then you got 1, 2, and so far. So that's the lowest number. So that would be bounded below. It stops. It has a minimum. So I just said it has a minimum. Any asymptotes? No, there's no vertical, no horizontal. Okay, now end behavior, we haven't really talked about writing it with notation. And so end behavior is about what the tails are doing. Where are the tails going? Because that's the end of the function. So we would say that there's a limit. It has a limit. As x approaches -infinity, a limit, as x approaches -infinity, it's going to where? As x approaches -infinity. So here's my x. It's approaching -infinity. Well, where's it going to? It's going to positive infinity. So as x is going here, what's the y doing? The y is going to positive infinity. So you would say it's going to positive infinity. And then we've got to talk about the tail over here. So as x approaches -infinity, y is going to positive infinity. And then the limit, as x approaches positive infinity, so yeah, as x is going to -infinity, where's y going? Positive infinity, right? Because it's up here. Now, as x is going to positive infinity, where's y going? It's also going to positive infinity. It would have to be down here if we were going to put -infinity. And that's how you talk about end behavior of the tails.